since I'm not going to be here today, you're going to watch this video over Lesson 13, which was going to continue to build on Lesson 12 from last time where we talked about reaction types. And since I'm not there and I normally ask y'all if you have any questions on these strongly recommended questions, we're going to go over most of them so that I can make sure that you do have all of the answers filled in before we move into talking about our usual lecture stuff, which is practicing what I expected y'all to bring to class ready. And then if you have any questions over this, on Friday at the very beginning, I'll devote 5 or 10 minutes to talking just about Lesson 13 to make sure we're all on the same page. So the first question says, in your own words from your reading, why is a precipitation reaction named as such? And in my own words, the reason why I've said that is because a solid precipitate falls out of solution. Okay, so when we talk about precipitation as far as weather, we're usually talking about rain, and the raindrop is falling out of the clouds, and it's precipitation, but it's specifically rain. And then in chemistry, when we react to things that are aqueous in nature, they have no solid in them beforehand, they are clear, though they may be colored, they're clear. Upon mixing them, a solid forms, and so that's the precipitation part. The next question says, using the solubility table 4.1, which is in your textbook, we need to predict whether sodium carbonate or calcium carbonate is going to form what's called an insoluble or soluble compound. And so we did this in experiment 2, I think, where you guys looked for the solubility of your standards and your unknown in various solvents. But this time, instead of looking whether or not something dissolves, we're trying to predict will something form. So I have my textbook, my OpenStax, ready to go. And we know that we're looking for calcium carbonate and sodium carbonate. So we have to come down here and we have to look for, we have our top part, which is soluble ionic compounds, and then insoluble ionic compounds at the bottom. And we see that if we look in the second column, that carbonate, CO3 2-, is in the very last half of table 1.4, and it says that it is going to be insoluble except for compounds with group 1 cations and ammonium. So this is our +1 cations. Okay, so with that information, let's go back to our notes. And our rule was that carbonate is insoluble, okay, so insoluble except with group 1A cations. Okay, so if I look back at my questions, sodium is a group 1A, meaning that this is going to form a soluble compound. It is the exception to the fact that these are insoluble. Therefore, calcium carbonate is going to be insoluble because calcium is not a group 1A, instead it is a group 2A. Okay, so calcium carbonate is very similar to the scaling, the hard scale you get in your water, like in the bathtub and things like that. So we can see calcium carbonate, and you usually use CLR, that kind of stuff, to kind of clear up that lime scaling. Okay, so you need to know table 4.1, and there are much friendlier versions to the eyeball out on the World Wide Web than this. And so I would suggest looking for a solubility table that you like, that makes sense to you. Oops, wrong one. And make some note cards. But you need to know the solubility rules. And the reason why is that you need to know them for my test is because on the ACS test, you're going to have questions about predicting solubility. So it's good to go ahead and practice knowing them now so that you're not surprised at the final that you needed to know these all along. All right, so in your own words from your reading, Why is an acid-base reaction named as such? And I said the reason why is because that is an acid plus a base reacting. So nice and simple. That is why it's the definition, is because that is who is reacting in this reaction. So on that note, what are the 6 strong acids and what are strong bases? So our strong acids are HCl, HBr, HI, HNO3, H2SO4, H3PO4. Okay, so you'll note that these have kind of a similar area on the periodic table, with hydrogen being the only exception. But remember, we talked about hydrogen being on the left and the right as a non-metal. And so you'll notice that chlorine, bromine, iodine, phosphorus, oxygen, sulfur, and nitrogen all kind of coexist. The one kind of exception to that area is that carbon does not show up in any of our strong acids. Now, for the strong bases, there are different rules depending on different authors of the text. So some will specify 6 strong bases, and some leave a more generic rule. And our author of the books, or our authors, leave the rules for strong bases pretty open. We don't specify 6. Instead, we're going to say that any group 1 and group 2 metals that are with what's called a hydroxide. And so this was one of your polyatomics, okay, which is an OH minus. So some examples are things you've already seen in lab and things I've told you that this is a strong base. So these are some examples. So you'll see that it's the opposite for bases, right? The acids are expressed with the proton or the hydrogen in the front, and in bases the OH will come second. Okay. So what 2 products are formed in the neutralization reaction? Well, what is a neutralization reaction? That's just another word for an acid-base reaction. Okay. And the reason why we call it a neutralization is because when an acid plus a base react, it forms water and a salt. And both of these things are considered to usually be roughly pH neutral. Whereas an acid and a base, we know, or I hope you know, that they are not neutral. They're classified based on the fact that they are acidic or basic. Okay, so in your own words from your reading, why is an oxidation reduction reaction named as such? Another term for oxidation reduction is going to be called redox. So it's kind of like the Brangelina type thing where you take one name and the other name and blend it into a new name. So redox. And it's named as such because electrons are lost, and we're going to call this oxidation, from one species, and those same electrons that are lost are gained, reduced, or reduction by another species. Sorry, guys. Species. Okay? So, again, like an acid-base reaction, they are going to occur in a pair. You're going to have oxidation and reduction occurring together. So, fortunately, our definition below definition above will help us answer this question, because it says what species donates the electrons. Well, we already said the electrons are lost in oxidation, so the species that is undergoing oxidation. And then the one that accepts it, another word for gain, is the reduction. The other thing is the Ra and the OA, which is reducing agent, and this is oxidizing agent. And so we'll talk about these two things and when we start practicing it Okay. All right, so 2 more questions. What are the rules for determining the oxidation number or state? Your book has a very long list with lots of descriptions and lots of examples. And so I'm going to make it a little bit more simple and kind of try to boil it down into just a few rules. And so the first one we're going to talk about is halogens. Okay, so this is our group 7A. They tend to have a -1 charge, okay, which we technically write them as 1 minus, okay. And then we're going to have our noble gases, group 8A, and these tend to be what we call neutral, so their oxidation number or oxidation state tends to be 0. Then we have oxygen by itself, so not the group, but just oxygen alone. It tends to have a -2 or a 2 minus charge. And then we have hydrogen, which tends to be a +1 or 1 plus charge. These two right here at the bottom tend to be true most all of the time. But not always, but mostly. Okay, so they tend to be true most all of the time. And then we have the group 1A, and these tend to be +1, and we have group 2A, which tends to be +2. Okay, and this comes from our knowledge about the periodic table that we've already discussed in a previous lesson. Okay, now if you don't see a specific element specified here, it's because their oxidation number or oxidation state can vary from what we said that they were based on the group they were in. So for example, we said that sulfur tends to have a 2 minus charge, but that's not always going to be true, that its oxidation state is going to be 2 minus. And this specifically is going to apply to covalent compounds. Okay, so when we have something that's ionic, we have the fortune of getting to treat it like we did way back when we talked about periodic table, which is that its number should match the column it's in based on the family. When we start talking about covalent compounds, because they're sharing the electrons and they're not being transferred, that sharing has an impact on the overall charge on that element in that sharing process. So these oxidation numbers, oxidation states, should have been a highlighter, sorry. This tends to apply exclusively to covalent compounds. But because our polyatomics are also covalent compounds that are found in an ionic compound, this also applies to polyatomics. So we'll see that it applies to covalent compounds, but that tends to only be true because of the polyatomic in that ionic compound. Okay, and we're going to get to practice our rules, and so we'll get to see this in action. So the last part of this chapter, this lesson, it's kind of awkward because it starts moving us into thinking about stoichiometry, okay? But we are not going to practice stoichiometry in this particular lesson, and so I don't want to cover it quite yet. The way the book had it organized, I tried to follow the order of the book, but you can see this is chapters 4.2 to 4.3, so this question should be the first question on your next lesson, which I'm pretty sure, you can see it's all filled in, that it is. Okay? Alright, so now I'm going to take a break and go ahead and start getting ready for the next video, which is filling in our lesson notes down here. But I'm going to take a break. Please take about 5 minutes and talk to your neighbor and make sure you have all this filled in. Ask them if you've missed something or you didn't hear something, and try to have this all written down. Let's see if I can zoom out a little bit before we move on to actually practicing the information.